Welcome to everyone! I'm glad to see you all in this 4th conference meeting on parametric environmental and smart solutions for building retrofitting, which is part of the PRELUDE Educational event series.
So this list of conferences are clearly recorded. That's helped the possibility to having access to them in future. They are also supported inside the PRELUDE project on the specific educational event series page. But before starting with the presentation, we recap the project itself. So the topic that are treated inside the European co-funded educational event series for PRELUDE Task 9.5. So the short recap reminds what PRELUDE is. PRELUDE is a project working on precision building operation, utilizing real-time data for energy dynamic optimization. So aims to support the development of solution, commercial solution connected to companies, but also research solution and public body interest point and discussion on advanced, innovative, small, low-cost technologies and solution for smart building, smart city, and proactive optimization services. One of the scope of the project is clearly to support the minimization of energy use through forecasted, proactive, a different level of modeling control of buildings in order to maximize the operational control and their efficiency from the energy and indoor environmental quality point of view. We also try to maximize the self-consumption of renewable energy on site and balance what it is called the energy community approach in the building domain. In addition to that, we support the improvement of comfort in different comfort domains, so visual comfort, air quality, and thermal comfort, maximizing for what it is possible, free building usages exploitation. So the potential of what it is given by the environmental condition to reduce for what it is possible energy needs by the system. The project is a modular approach because it developed a platform, centralized and platform to manage multi-data sources, and that integrate a lot of modular technological, when you can say, supporting model developed by partners inside a same middleware solution, which is the Fusi platform supported by the Hemtech company. Several of the PRELUDE models uses historical data. In some cases, they directly use it to feed white box modeling approach. In other cases, they are used to feed machine learning. Okay, so black box approaches, forecasting, or gray box model of different levels. Especially the next event, we will focus on the integration of this type of system. In addition to that, among the proposed PRELUDE technology, we remind to have an idea where is the background on which we're speaking about. The integration of project middleware of different data sources, which looks to be simple. It is not, like topic domain. The dynamic programming potential exploitation through optimization of forecasting and white box modeling. The indoor-outdoor correlation model developed by Brunel University, supporting weather correlation usages in building in a sort of post-developed black box model. Weather and radiation prediction model for forecasting, occupancy profile model forecasting, again in different approaches from machine learning to different approaches in the field. District heat integration model to support district heating management. The possibility to support renewable energy communities, renovation roadmap, and this is part of the presentation of today that we will see together. Other usages connected to the renovation roadmap in supporting parametric and sensitivity analysis in data-driven simulation, okay? And in this case, we will see another example for retrofitting in our case. The integration of what we can say climate change resilience, environmental impact, life cycle assessment, life cycle cost. This is another aspect that we will treat together today. The support on dynamic energy forecasting, comfort energy efficiency optimizer and customizer graphical user interface with feedbacks, predictive maintenance, measurement and verification supporting for optimizing energy system in buildings, aggregation model, and other aspects. All these things and solutions are tested under different demo cases in European countries, from Denmark to Italy to Switzerland, Poland, and Greece. And in a very, very advanced living lab building, which is an office building. It's one of the most advanced living lab office in Austria, and one of the potentially higher level smart building in between the smart building lab, living lab series in Europe, which is Austin Pinkefeld in Austria by FBPAR. This support clearly the fact that all of this topic will be translated into communication to the interest party and to people studying at university level, not only professionals, also people studying university level, this type of topic, to have an idea what arrives around Europe and outside Europe, in some cases for some speeches inside this topic. So today, we have seen the list before, we will focus on building retrofitting solution, driving what? The possibility of, to experts, no? To have an idea what they are doing, which are the difference in between the choices, or we can support expert choices for environmental analysis, so life cycle also, cost optimal analysis, and energy correlated analysis also. The event today so focuses on building retrofitting, focusing on design management and innovation in the building retrofitting, analyze with two presentations, supporting platforms, helping designer in easily having access since early design choices, since the beginning of the process, to what may be or what can be the driver, the better arrive to a cost optimal, energy optimal support. So supporting their choices in design. Include cost analysis and also potential life cycle assessment issues. And the speaker of today are recognized as experts working in the field in different countries around Europe and near Europe. Especially today, that's our program. After my short presentation, we will go inside a speech held by Dr. Nathalie Dumas from the ESTIA company, based in Switzerland, Lausanne, that will support and describe the EPIQR Plus methodology and the platform, which is a web platform, very accessible. That's very, very interesting. It's a method and a platform support efficiency diagnose. So before the retro, what's the elements, which are the deterioration of components and buildings, and very fast help professional to have an idea of the cost of renovation, a different level of renovation level, and the related CO2 emissions. That's very, very urgent because we know that Europe is pushing more and more the need to have CO2, okay? Active production of CO2 by the energy use and passive production of CO2 by what was the embodied carbon, okay? Approach. That's a start to becoming regulation, okay? So it's clearly an open issue now to do that in a fast way. So Nathalie Dumas is an engineer at ESTIA. Her interests clearly focus on the energy environmental performance, on the built environment point of view, focus on building scale, includes both professional and industrial research that's inside the ESTIA company. It's a very multi-visionary approach from research to application in the industry and to support of public bodies. And peculiarly, she will present the EPIQR platform, very user-friendly simulation tool to support fast community and retrofitting action for professional comparing solution and supporting the identification and shared way of the best interested approach. After the speech of Nathalie Dumas, we will have the speech of Professor Valentina Stojceska from the Brunel University in London, Great Britain. She will have a very interesting speech again on building a greenery future that in this case will support and will show the adoption of environmental sustainability inside the retrofitting and renewable energy integration in buildings through a life cycle assessment study. That's again, we are in the line of this expanded, I want to say in a simple way, environmental concept. So not only energy needs, not only energy consumption, but what it arrived during the whole life cycle of the building. So production of the components, installation of the components, lifespan, so consumption of the building, and after end of life. And that's again very, very interesting because that's arrived from an expert in the field, associate professor in this very interesting university in London, that support the adoption of this type of things and the integration, life cycle assessment analysis inside buildings in the PRELUDE project. At the end, before open to have question and answer to question, we will have a presentation led by the POLITO teams inside the PRELUDE project that will be about PREDYCE, which is a new, we can say, parametric sensitivity multi-usages platform managing Energy Plus, like an interface, Python-based, that supports, for this specific case, a new model that uses cost-optimal analysis inside the sensitivity analysis model to support optimization to a professional, giving an idea of which action are more or less impact on the energy point of view and also on the cost point of view. So supporting cost-optimal identification. That again is very, very interesting, because one of the issues that we have, at least at the beginning of early design, is how to orient our choices not in a sort of explicit way, not only given the fact that I'm working 20 years in retrofitting, so I start with changing window, for example, okay? Because potentially the specific building, the specific content will benefit more by another action, by another list of actions that the earlier you identify them, the better it is in terms of cost saving, and especially in the possibility to change your design in advance. This gives a bit the idea what we will speak today. And after, I hope to have the time for question and answer, or better that the auditors will be interested in the topic and will ask to the speakers something. Before ending this introduction, this educational event series, and I will suggest you also to follow on the 16th of January, the next event, which is about proactive building optimization, which is about big data usages, monitoring the buildings. Okay, but this series of events is part of a larger work in educational and citizen science approach that not only involves students, but also population in a multi-action event. One of the list of things done is this educational event series, but in addition to that, we had involvement of students for the Polytechnic University here in Turin, but also in the Piedmont, in different school level in the Piedmont regions, thanks to the Piedmont Educational Division, to support indoor environmental quality monitoring, to activate the people in a citizen science action, to have feedback and try to operate windows and things in the school, for example, to maintain indoor environmental quality according to Censo. And in parallel to that, there is also the organization and the development of indoor IoT platform and sensory platform done by students, for students inside this approach. Clearly, we have a GitHub organization, the possibility to have access to some of these topics in open field. So now I will leave the floor to Nathalie.
Hi, so yeah, my name is Nathalie Dumas. I'm working at ESTIA, like you said, a consulting firm specialized in building physics and located in Lausanne. And in this short presentation, I'm going to describe you how the new version of EPIQR works, what are the latest updates, and what it can be used for. And first of all, EPIQR stands for Energy Performance, Indoor Environmental Quality and Retrofit. It's a building diagnosis method born from a European project between 1996 and 1998. In its first versions, the EPIQR software and EPIQR Plus method that succeeded it were desktop tools, allowing a precise diagnosis of the state of deterioration of an existing building and the elaboration of renovation scenarios, including the different costs of the necessary intervention works. As part of the PRELUDE project, the EPIQR desktop tool moved to a web platform, allowing anyone to easily diagnose a building renovation with reliable costs from anywhere. Secondly, and also through the PRELUDE project, new elements with their relative costs have been added to the method to take into account smart technologies or energy optimization actions and also renewable energy sources. And finally, to help the residential building stock to fit with CO2 reduction targets, the new version of the method also includes the CO2 indirect emissions of each refurbishment action. This EPIQR Eco method will, after finishing its implementation, also be able to take into account reuse materials scenarios. The first step of a building diagnosis is the completion of building informations in the first tab. contact details for both the building and the owner can be filled, as well as visual building informations like pictures or plan of it, as we can see in this capture. The second tab, or modeling part, refers to the building dimensional and cost coefficients. Dimensional coefficients, so on the left, are necessary and define the relation between one specific value measured in the baseline building and its corresponding amount in the diagnosed building. And those relating to costs allow to adapt the cost of each intervention, including material and labor, to building specificities like access or height, and to the economic system of the geographical area or country. In the evaluation tab, the whole EPIQR structure and coding principle defined by the method is summarized. The building is first decomposed in 10 macro elements, which are either, for the first, architectural, and the last one, technical ones. Then, by clicking on a specific macro element, here the facade and balcony, its component parts or elements appear. The plus sign adds the item to the diagnosis, so the plus sign on the right. And the light color elements have not been added yet. For example, the facade decorations is not being diagnosed for now, and with no cost associated. Similarly, by clicking on a specific element within a macro element, its component parts or types appear. So here, for the exterior walls in plaster, we can have different rendering listed here. Each element type can be diagnosed through the selection of two criteria. The first one is the degradation degree, and the second one is the intervention level. The degradation degree qualifies the element's current state. Pictures can be added on the right to remember it. And the intervention level qualifies the work to be done to this element. So between 0 for no work to 3 for complete replacement. And we can also add here a ratio to each element to adapt them to the project reality. For example, if you have different type of facades, you would like to add each of them here. And then by clicking on the cost below, here, the selected intervention level, cost breakdown with work details. The unitary cost of the relative quantity here are detailed and help to understand which specific interventions are taken into account in the total costs. So the total cost here, it's the 8,000. And if needed, again, a ratio can also be applied to the total cost. So the ratio that we see here, the 50%, can be changed. And several renovation scenarios can also be added by clicking here on the right corner of the intervention level tab. And also for some element type, improvement or adaptation work can also be selected. Here, for example, you have the possibility to transform the facade into a ventilated one and adapt the cost of it. And then in the last tab, the publications one, you have the result for each cost scenario and for the overall diagnosis that are available in the form of reports. And still within the PRELUDE project, about 10 of smart technologies or optimization actions with their relative cost have been added to the database. Most of these new elements are located in the technical macro elements, such as here you can see electricity, or just below the intake one. To list a few, the addition of a storage element that you can see here with its relative costs like a battery or the installation of charging station for electric vehicles, can now be linked to the photovoltaic installation and added to the total cost of the diagnosis. And similarly, optimization energy contracts, as well as the installation of energy meters, are now available in the database. So here it is for the heating macro, where you can see that you can add implementation of an energy optimization contracts, etc. In addition to costs, several energy performance parameters can be entered into the platform, such as the energy efficiency class of each macro element that we can see here. So in different colors and length, depending on the quality of the element. Or, for example, the heat consumption index, which here comes from the actual building consumption. The latest software updates, but not the least, is the calculation of the indirect CO2 emissions of each renovation work, named EPIQR plus ECO. So these results are derived directly from the diagnosis coding. No extra time is needed, and they are presented in the same form as cost results. So here we can see this is the actual state of the building. And for the first scenario of renovation, you have the cost and below the CO2 indirect emission of each interventions. This is the second scenario here. And they permit to compare different renovation scenarios between them with another criteria, so not only the cost. And they also permit to compare them with the energetic standards of the country. So the energetic standards value are at the end here, and you can see if we are on the green side or the red side of this standard. The calculation of the direct CO2 emissions of a specific renovation is actually under development this platform, as well as the version for all building affectations. For now, it is only for people, houses, I would say. And the EPIQR plus ECO method, validated this year and currently under implementation, also indicates next to the renovated element whether it can be reused or not. Here you have a list of potentially recoverable elements, here with their relative quantities linked to scores in different categories. So the state condition of the elements, the removal difficulty, commercial, economic, ecological, and architectural potentials. And you also have available the informations on logistics or packaging recommendation, for example. So that's all for this presentation. I don't know if you have questions now, or maybe we wait for the end of the presentation. And thank you for your attention.
Thank you, Nathalie. I don't know if you just have a question now, otherwise, clearly we will have the question session at the end. No one has a question right now, otherwise we pass it by the hand. Hello, Valentina, you need to unmute the phone. The microphone.
Hello, everyone. Can you hear me?
Yes, great.
Okay, so yes. Good afternoon, everyone. My name is Valentina. I'm employed by Brunel University London as a reader, and I'm involved in PRELUDE project as a co-investigator. The principal investigator is Professor Maria Colocotroni. And today I'm going to discuss about the environmental sustainability about the buildings and how they can be improved with retrofitting and renewable energy integration. The overall presentation is including the building sector building sector. I'm going first to discuss about the building sector, how much the building sector affects the environment. I'm going to discuss about the retrofitting of the buildings and how the retrofittings of the buildings could help with reducing greenhouse gas emissions. I'm going to discuss about environmental assessment of the buildings and what kind of tools could be used for that. And at the end, I'm going to discuss about the, we'll introduce a case study of the building, which is based in Geneva, and this building is part of the PRELUDE PRELUDE project. In terms of the building sector, I would like to provide a little bit of information about the responsibility in terms of energy consumption. About 40% of the energy consumption in building sector is responsible about 40% of the all energy consumption. 36% of the energy-related greenhouse gas emissions are coming from the building sector. 50% of the resource extraction and consumption. 30% of the waste generated comes also from the building sector, and 75% of the existing buildings in European Union have been classified as energy inefficient buildings. Around 85 to 95% of all those buildings are expected to remain in EU by 2050. As a result of that, the European Union member states agreed that by 2030, all new buildings must be zero emission buildings, and by 2050, all existing buildings must be transformed into zero emission buildings. So one of the ways of improving this environmental assessment, environmental impact of the buildings is to introduce, retrofit the buildings. For that reason, there are lots of different measurements that have been taken to reduce the environmental impact of the buildings. And we are familiar about, for instance, improving the insulation, the ceiling of the buildings, improving, for instance, the roofs, floors of the buildings, to reduce, for instance, the heat, to reduce the heat transfer of the loss of the heat in the buildings, and also to different types of sealing of the gaps and cracks to prevent the buildings. Installation of the green roofs and walls is also something that has been considered. Replacement of the windows and doors with more efficient ones. Using energy efficient lighting, for instance, replacing of the bulbs with energy efficient LED, or installing sensors, for instance, to control the lighting system during occupancy. Another thing is upgrading of the mass system, upgrading of the ventilation, air conditioning system, and in terms of making them much more highly efficient, and use energy renewable sources like solar energy. That could be some wind energy and also biogases that could also replace the existing energy sources that are relying on the fossil fuels. Implementing smart building systems is also something that is considered in order to optimize the energy use. Using, for instance, sensors or, as I mentioned before, about lighting system, also to improve the building efficiency. There are also another elements like, for instance, water efficiency, reducing waste, that are also contributing to reduction of the greenhouse gas emissions. But also another thing that which is very important is also behavior, improving the behavioral changes and occupants' engagement in terms of how the energy is used, mainly how the energy is used, and also to develop some good energy saving practices. But this retrofitting of the buildings is not always easy to implement, and very often we are facing with different types of issues, and that issues could be related, for instance, with the cost consideration. For instance, the retrofitting could be expensive, and there is also some kind of hesitation by the owners about the investment of these energy inefficient buildings. And also due to the cost that are involved, for instance, cost of the materials also, and that's also something which could cause lots of issues. Another thing is the technical challenges could be also, especially if we have older buildings. And that's also something that needs to be considered, because not all the buildings, new or old buildings are the same. They need different types of approach. There could be some regulatory barriers as well in terms of when it comes to retrofitting implementing retrofitting measures, and also implementing of energy efficient technologies. And that also depends on the place where the buildings are based. If they are in the European Commission in different countries, even different countries in the European Commission have different approaches how they're dealing with this with improvement of the energy efficiency of the buildings. Could be also lack of incentives. There are different, some regions have more financial incentives, some regions have less, or some countries have more or less. And also there is also kind of limited awareness that the building owners or stakeholders are not fully aware of the benefits of retrofitting, and they may need to invest in that, or for instance they underestimate the potential savings that can come from retrofittings. And we mentioned about cost consideration, also financial barriers. Financial securing funds for retrofitting projects can be also challenging, particularly if we have some kind of small businesses or property owners with very limited financial resources. Also, we need to take into account the climate change, because that's also something that is affecting the retrofitting of the buildings. We know that about some places in the world where the temperatures are much increased, and we have another where the temperature are much lower. So it is important for all to take into account all these issues, challenges that are involved with retrofitting of the buildings, and that's why in order to improve the environmental assessment of the buildings, and we would all like to see some buildings like this one, which we have lots of greens around, and we can see some modern building that has been built, but unfortunately we have to work with the old buildings, and we need to discuss how we can improve them. So to be able to do environmental assessment of the building, we need to identify the current environmental footprints of the building, and also after retrofitting of the buildings, in order to find out as much as we can, of course, how much of our retrofitting affects the environmental footprints. And there are different aspects of that. And I would like, when we talk about environmental assessment of the buildings, I would like to introduce a life cycle assessment framework, which is involving 3 different stages, like a goal and scope definition, inventory analysis, and impact assessment. And this is a standard life cycle assessment that could be used for industrial processes. It could be used for different for assessing of the environmental impact of different places, of different processes, but also applies to the buildings. This is you can see the 3 stages at the middle, where we have goal and scope definition, inventory analysis, and impact assessment. It is all of them are very important, and you can also see what is involved in all these three stages. In assessing of the scope, it helps us. First, we need to know why we are doing this work. So the scope is important, that we need to establish the system boundaries and limits to life cycle assessment. For instance, if we use life cycle assessment to compare what happened before retrofitting and after retrofitting, how they're sustainable they are, we need also to set up at the very beginning. Or, for instance, we can maybe make some comparison between the buildings. That's also something which is set up in the goal and scope definition. And also functional units, which is very important in terms of buildings. This is very important to be set up at very beginning. And that could be based on the amount of energy that is consumed or used by the building, or it could be the building area. The most intensive process is inventory analysis, probably the most difficult, when we try to find out all the data that we related to the processes, or in this case with the buildings, and we need historic data. So we need to work on the data collection, and also we need to collect all the data, and sometimes we're using energy bills, sometimes using the other utility bills. And we have at the end the impact assessment, and after this coming interpretation of the results, and also communication about the results. We can see that all these different sections or stages are reverse processes, so we can always go back and improve the process, and after that make again the calculations. Or use some of the softwares. So when we talk about this life cycle assessment, it is important that we set up the system boundaries of the buildings. And you can see on this picture, you can see the standard EN 15978 from 2011, where we can see the different stages of the buildings. And this part of the building is including product of the building from very beginning to the very end of the process. So you can see different stages, and which starts from very beginning, where we have the materials and transportation involved, and manufacturing of the building, construction process, use of the building, and end of life. So in how many buildings we can apply all these system boundaries where we have end of life? There are probably few of them, because the old buildings are normally retrofitted or they are improved, and we are focusing more on the assessing the environmental impact of the life buildings, of the buildings that are in use. In terms of, so we have these system boundaries. When we have the system boundaries of buildings, we mentioned about collection of the data, of the inventory analysis, which is part of inventory analysis that we mentioned in the previous slide. After that, we are thinking about how to use the data, how to analyze in order to do the environmental assessment. There are a number of life cycle assessment tools that have been used for assessing of the buildings, and we can see on this slide, we can see different types of tools. The most used are Gabi and CIMA Pro. They can cover all three aspects of sustainability, like environmental, economic, and social sustainability. We can see also another types of life cycle assessment tools, which are applicable more for the buildings. and depends on the type of the building that we are analyzing and what kind of information we want to get, and the impact assessment methodology will depend also on the software that is used. And we can see the building-specific life cycle assessment tools, which involves, for instance, Athena, and we can see, for instance, Athena and BEES. They are popular building assessment among building, which is also having life cycle assessment tools. And they can provide valuable information about the impact assessment of the building, or, for instance, information about the footprints of the buildings. And we can see there is a number of other softwares that could be used, and we can see also for all of them what kind of information we can get, like, for instance, cost, environmental impact, greenhouse gases, for instance. That all this information could be obtained from this type of programs. And in the next few slides, I would like to introduce a case study, and the case study is a part of PRELUDE project. It is related with a building which is based in Geneva. The building has 9 floors, has been built in 1962, and it has originally had 48 apartments and 7 floors. However, there was some building work ongoing before the partners joined PRELUDE project. From 82 apartments and original 7 floors, they built a few more apartments and 2 additional floors. So the overall the apartments are now 58 with 9 floors. A number of renovations and retrofittings, refurbishment were carried out in this building, and I think that was between 2020 and 2021. And the main reason for that, of course, was to reduce energy consumption of the building, and in order to get some zero building, to bring it to the zero emissions. So a number of refurbishments were included, like where we said, additional 2 floors of the building, insulating the walls and the roofs, triple glazing windows have been installed in the building, PV panels on the roof, and also renovating the technical installations of the building. So what we mentioned before, we were using for this building life cycle assessment, and the first thing that we have mentioned was the goal and scope of the study. So the goal of study was to carry out a life cycle assessment on this building, and estimate the environmental impact based on the energy consumption of heating and domestic and hot water before and after the renovation. And the scope of this study was the scope of this study was to specify a functional unit, which we took into account the amount of energy that has been used, and energy sources, input energy and output energy. For input energy, we took into account the sources of the energy before and after the scenarios. Before the refurbishment, the building has used energy sources for heating and domestic and hot water, and also a gas burner, heat pump, energy produced from PV panels, and were installed of the roof. And with output energy, we have considered that before and after refurbishment. Before the refurbishment, all radiators in all 7 floors were heated by a gas heater. As a part of the refurbishment process, a total of 150 sensors were placed in the building, primarily in the last 2 floors, and they were monitoring the temperature, pressure, electric consumption, electric flow, status of the gas burner, heat pump, and gas counter. These 10 sensors were placed in the apartments in the last 2 floors, one in each apartment, monitoring the energy consumption. And we can see now the system boundaries of the building, and this building is before and after refurbishment. I would like to emphasize that this is we considered the life cycle assessment on the usage phase of the building, because the building is used, and we can see that system boundaries with before refurbishment and what kind of energy sources have been taken into account, and after refurbishment. And the usage phase between and after the renovation of the building. And a number of data and also the historic data have been received from the partners. This is something which comes from PRELUDE partner, and we considered before refurbishment. You can see the values that we considered, and you can see all these input variables that I have already mentioned. Value of the buildings, unit, and for what they were using. And also EcoInvent database have been used. We were using EcoInvent 3, we were using CIMAPRO, and we considered this for the gas supply, heat central or small scale natural gas, heat pump, and PV panel system. We have using the database for EcoInvent 3. And in the next slide, we can see the more data like variables before PRELUDE and during PRELUDE or after PRELUDE project. And again, we had 3 different scenarios which came before PRELUDE and during PRELUDE. Annual production of the power for each renewable system is given in this table. So we were more focused on the retrofitting of the building, but taking into account the use of the renewable energy and the other the renewable energy. So we can see some of the data about characterization results of this building. This data come from CIMAPRO simulation, and we can see there are 13 categories that have been taken into account, and you can see all of them. There was, and you can see also, I hope you can see it here, it is one part which is says before heating, before refurbishment, scenario A1 and A2. And you can see the differences, and there was a difference found between before and after refurbishment of the building, and the reduction, the largest reduction of the global warming and ozone formation, and also fossil fuel resources was seen at scenario A2. It was also interesting to see that the impact of ecotoxicity categories from 7 to 12 was greater after refurbishment conditions. And this is probably because it is related with the utilization of the PV panels and also the heat pumps. The next slide shows the damage assessment. This was similarly as the figure shown before. 3 aspects were considered: human health, ecosystem, and resources. And it was interesting to see that the reduced damage impact of the 2 refurbishment scenario before and after there was some difference, but scenario A2 gave much more promising results with a reduced impact in all categories. In this file, we can see the characterization results of the optimization scenarios, which involves different renewable energies. What we got, it was that the greatest impact for these categories were related to the global warming and ozone formation, and also fossil fuel resources. And this was as a result of combined heat and power. And also we've seen some effect of using of the photovoltaics, which they have a greatest impact on terrestrial toxicity and human toxicity. While electricity from the grid affected the most of the mineral resources. And again, we have the damage assessment, which shows the percentage of three main areas again about human health, ecosystem, and resources of different renewable energies, specifically of photovoltaic, wind turbines in combined heat and power, and also heat pumps, and relative to electricity from the grid. It is also what we got from those results, that in all three main areas, combined heat and powers were associated with the higher SGP input. And the lowest impact of the three areas was from the wind turbines, followed by HP. So that's it from my end. I thank you for your attention, and please let me know if you have any questions.
Thank you, Valentina. Quite interesting, yes, like approach. I don't know if you have a question yet. Otherwise, again, we'll leave question to the end of all of the three presentations. So right now we have the last presentation that is from POLITO side. In the third presentation, we'll come back again to a simulation platform that support massive dynamic energy simulation in Energy Plus, in this case, to support professional in choosing retrofitting strategy for a specific building using sensitivity analysis and optimizer. The scope is not only to analyze the less active consumption of the building during the operational phase, but also to analyze the cost optimal impact of the different retrofitting choices. In the point of view of the domain, it's clear that including energy and environmental performance, so we not only look at energy, we may look at free-running building operation. So how will be the thermal comfort in this building when we apply, for example, a specific series of packages of retrofitting action that is perfect for winter when we are bathing, but potentially is not working well for summer when there is no cooling like in traditional Italian buildings or Mediterranean buildings, but we need in any case to live and for what it is possible to guarantee the comfort without asking to install extra cooling system that will consume a lot. So roughly speaking, we will look at this constant that is essential to analyze energy and environmental performance of building and building design or retrofitting design as early as possible. Now this is entered in the green BIM, for example, domain and others. That is clear that the early phases, the early design phase will include design change possibility, the more that will be the better, because in this case we can change more because we do not have already done the design, okay? And the cost for changes is very low, so you really have the maximization of this assault. But to do that, it's essential to develop tools that allow designer, which are not coding expert, potentially the majority of the audience is today, okay, and need to perform fast and easily accessible multiple simulation to detect if a specific choice of in a specific direction in the building retrofit is a good approach or not, in an explicit performance-driven approach, rather than applying the typical traditional, implicit approach that support, in particular, choices which may not be given or supported by data, but only by past experience. In addition to that, there exist some tools that do that. You also experience, out of the audience, let's experience BESOS, which is an energy class interface support, sensitivity, optimization, surrogate modeling, and so on. There is others like GIA class and other potential support that allow to have master simulation, but it requires some highly specialized knowledge. So it's clearly interesting to see the possibility to see a platform developed inside and by a FT expert, but that is also usable in a sort of user-friendly, semi-user-friendly approach for transdisciplinary vision in this cost-optimal domain. So the objective of this presentation is to show a new methodology for cost-optimal analysis in building based on an innovative Python-based energy class interface, this PRELUDE, that we will see shortly what it is, to support since early design or since intermediate phase of design the choice of the correct service for retrofitting. And we will discuss this application using a real demo building, which is a building located in Turin, inside again the demo of the PRELUDE project. We will see the structural presentations approach and methodology. After we go inside what it is, the PREDYCE simulation platform, we will see what is the domain of this PRELUDE Turin demo case. And after we see the application for retrofitting action definition, cost databases, and selection of key performance indicators that we will use. That's clearly how open and will be defined, at least retrofitting action and selection of KPIs by the end user. So inside a very large list and database of potential actions pre-built in the code. We will see the result, and after we have some conclusion. Broadly speaking, and before giving the floor to engineer Francesca Fasano that will show you the platform in deep, we only remind, broadly speaking, which are the general approach. Now we have an architect and engineers is asked to do a retrofitting solution for a building, and will develop this design solution. Broadly speaking, generally do a building inspection, more or less following a protocol, and after define clearly the definition of the boundary condition. What action I can do there according to the local regulation, what I need to do according to national European regulation, what I can do in terms of cost, because clearly that's also a domain, what could be the application in the specific constraints. But broadly speaking, in general, this clause and a sort of implicit design approach, they clearly give and left open the fact that we are really select the best solution or the solution that perfectly works, I don't know, in this typical climate, in this local microclimate conditions, or why not, will be resilient to climate change in the future. So that's clearly support the fact that we may have alternative visions that help the development of the final design choice. It's done by the design, it's done by the company that support these things, but through the adoption or a more coherent and performance-driven vision. They use what? Building modeling, retrofitting action variations, sensitivity automatic analysis to support and potentially analyze which is the impact of the different technology on the field. And this is a bit more advanced than what some of the current tools allow architects to do, not because we are really in a sensitivity analysis, we are in the dynamic simulation domain, so without the problem of semi-steady state approaches, the blocks, the sum, thermal masses, or this type of, we can say, transition simulation part, we have the possibility also to test control logic and the possibility to test more advanced solution in this hybrid vision of between passive and active cooling, for example, this type of solution. And that's clearly suggests optima to support the design solution, or at least to have an idea on the energy, on the thermal comfort, on the cost point of view, which would be the direction that will be given and taken by a specific choice in the building design.
Now we start looking into a specific case study we worked on recently. However, the methodology that we have followed is independent on the demo case and usually comprehends these steps. First, modeling the building demo case, and then calibrate the building to align it with its real behavior, especially concerning the free-running indoor temperature. Then we have to define the boundary conditions of the model. So, for example, which is the occupancy and other set points and schedules, the retrofit parametric actions, and the key performance indicators. Finally, we can perform the parametric analysis and manage the results. Today, we will focus on these last 3 steps. But before deepening them, I just introduced you the platform that we've used to perform the parametric building energy simulations. And also the calibration process, of which you can see two images here, but we will not deepen this step today. So, PREDYCE is a building simulation supporting platform, which was funded under 2 European projects, EDICE and PRELUDE. I already introduced it to you about 1 month ago, so briefly now. It is coded in Python and structured in independent modules, which main purposes are: first, allowing automatic editing of building models in IDF format. Then, compute several KPIs, both climate and building related. Perform parallel energy class simulations, and finally also generate weather files from data coming from different sources. The combination of these modules allow the definition of several usage scenarios, which allow to simplify and also test several methodologies and processes. For example, here we are doing building and also climate parametric analysis, which can eventually be coupled with optimization algorithms. And we also use the calibration support module, which allow to support the building verification process in a more automatic way than how it is usually performed. Here you can see an example of PREDYCE aggregate output. And as you can see, it is very similar to the output you can get from Bezos, if you've already used it for the laboratories, with the simulation reference index on the rows, then a first set of columns identifying the variable parameters, and another set of columns with the KPIs. Moreover, PREDYCE allows for each simulation to retrieve time series KPIs with the desired time step and to generate plots. For example, you can see 1D and 2D energy signatures, adaptive conformal model points distribution, an example of a carpet plot, which could be generated with several variables in input, and also the carrier plot. Now we start looking into today's application. The demo case is a multi-story residential building located here in Turin, which features characteristics in line with most buildings constructed during the 60s and 70s. It has never undergone a renovation process, except for measures taken by single tenants, so not in a uniform way. For example, substituting windows in some apartments or installing some cooling split units. The building has a north-south orientation with mainly living areas on the south and bedrooms on the north. In this building, 8 of 27 apartments are monitored under the PRELUDE project, and so they have allowed to calibrate the model. Okay. Here you can see the list of retrofit actions that were chosen for this demo case and how they can be translated into an input JSON file to the PREDYCE platform. The considered actions include adding an insulation layer to boundary walls and to the roof floor, substituting the window system, and also adding automated shadings to the south-oriented facade, change the lights both in the apartments and in the common circulation areas, upgrade the heating system, and systematically install a cooling system in all the apartments. And finally, the addition of detached mechanical ventilation units, which could allow indoor air quality improvement and heating savings in winter. And lastly, also adding ventilated cooling in summer to the bypass of the heat recovery of these machines. Okay. Here instead are listed all the KPIs retrofit to evaluate the performance of the different retrofit solutions. Among them, some are aggregated yearly values and others are time series or plots, which allow to determine the meaning and behavior of specific simulations. KPIs allow to evaluate three main performance aspects, which are consumption of heating, cooling, lighting, and mechanical ventilation units, costs, and thermal comfort. KPIs related to cost are dependent on the selected demo case, clearly, and hence needs to be used accordingly. Also, maybe you could notice that to reduce the number of simulations, the change in the heating and cooling COPD, so performance coefficients, is evaluated as a post-analysis. So the numbers of simulations could be drastically reduced.
Okay, the first steps is to develop the cost database. What does it mean? We don't need to develop each time for each building, but clearly, as we also have seen, costs are generally referring to the local area in which we work. So maybe member states in Europe, for example, maybe a specific region, like for example, maybe in Italy, and so may require the fact that some of these costs need to be taken or adapted according to the specific place in which we do the building analysis. In this specific case, thanks to the work of Dr. Davide Mecca Cici, clearly we have defined a cost database which is set for the Piedmont regions. So the majority of the action comes from the regional price list of materials, of installation, so the number of people putting on the specific material with a different level of thickness of the insulation, for sure, is not only a parametric cost of the insulation, it's also a change in the cost of the installation, because till a certain amount is a cost, above a certain amount means different fixing point, more time of working and so on. Plus the maintenance cost over a 20-year lifespan that may change according to the type of building. But broadly speaking, we put to this type of things, considering that in this period we don't do other larger retrofitting approach. Some of the costs may not be found in the original price databases or in other databases that need to be developed by market estimation. That means calling, asking to different companies and making a sort of average around what we get with specific approaches. Like, for example, for the detached mechanical ventilation unit, okay, or this type of things. This clearly supports the definition of the initial cost, the investment, okay? In addition to that, clearly we have the operational cost that need after to be considered not only for a single year, but for the lifespan of this intervention. That in this case, we set to 20 years. So we have 20 years of operational cost, clearly with the adaptation of what it is needed to bring back the cost, to actualize the cost in order to have the idea of what arrives in the long term. Okay. In this sense, the energy cost of energy, the cost of the energy is supported by an average of the last energy bill in national databases. We support the national authority, okay, for energy and cost in this sense, and also we ask to hear an SPA, which is part of the project, it's part of the hearing companies in this sense. And thanks to that, clearly we will be able to analyze the total primary, to analyze and post-elaborate the KPIs that we are interested in. So the total primary energy, so not only the final energy for natural gas, if we have a specific heating system, or if you change it to electricity, if we try to analyze and envisage what may arrive in Europe in 10-50 years, now with the exchange of natural gas with electricity. But in addition to that, we also pass this final energy use to, with the specific cost split, to primary energy factor to also have an idea what is more near to what you may look, for example, in an energy label, okay, in terms of type of output. So we apply clearly the COP, the coefficient of energy performance in terms of energy efficiency ratio for cooling, the COP for heating, plus the lumen, etc., to radiant electricity, multiplied by the specific factor according to the source used in the final energy. After we pass to early operative cost, because we analyze not only the initial cost of the investment, but also the cost of operation. So according to the energy needs, by final use, clearly we will have a cost, that is the cost of the gas, which is the cost of the electricity, which is the cost of the energy fuel that we expect to use, clearly for the single year, and after actualize it with the discount rate, that in this case we set to 3.5 by a concept looking at what arrives in the market. And clearly, thanks to that, we will be able to calculate also the total cost and the return of the investment. On this point of view, we support hence this simulation that I said before will look inside sensitivity analysis for all of these actions that may be more or less. In this case, we select a more diffused one, also looking with the panel involved in this Turing demo case. And we analyze the system working with HVAC on, so in mechanical mode, and in the free-running mode, especially to analyze the differences, especially for summer in this case, now for what arises with and without the mechanical cooling, for example. And in this case, clearly we check the HVAC and free-running under the typical meteorological year, which is what is the climate, the typical climate of the region. Is exactly what we, for example, develop in some cases of exercise to support the choice of the best design solution. But also we analyze one case of the same building under an actual meteorological year. So a true monitored weather in Turin, thanks to our cloud-connected metro station, to support and check what will be the resilience of these choices under an heat waves. I don't know if you know, but clearly in the past year, and also this year in a way in Italy at least, we are envisages quite long heat waves. So very hot summer, or very hot summer period, as in Italy is larger and peculiar. And this support the possibility to test if the choice under the typical climate, how they will react, for example, if we would be expressing heat waves or more critical climate conditions like maybe in the future for climate resilience. And these are the type, we'll see some types of new outcomes that we are developing in our methodology. This is one of the first. It's not so far to watch, also maybe use it in some resources there, but in any case, it's the development of a heat map that show, this is the typical, the climatic data, like we do for building retrofit general analysis and energy point of view, but this is what? This clearly gives to the professional a vision of how would be the impact of the different retrofitting choices that you see on the x-axis, okay, with respect to what are the changes on the y-axis in which we have the performance indicator identified before. So, for example, it's totally clear that when we work with the thickness of insulation on the wall, you will have a direct impact and variation on a reduction, okay, on the heating needs, quite evident. Okay, if you look at heating need reduction, you also see that the installation of the touch mechanical ventilation unit with heat recovery as also a very positive approach, because this would reduce the losses when opening the window for the quality. Okay, but in addition to that, we also see, for example, that clearly the installation of the mechanical ventilation unit will increase the electricity consumption of ventilation because before was not there. Okay, that's give a bit the idea. But broadly speaking, what it is interesting to see is clearly that we can also see that the approach of lighting, that is all the impact of the lighting consumption. Okay, that is, for example, what we see in this line here. So lighting consumption, lighting changes, but clearly lighting may also have a sort of impact, of what it is, the byproducts in terms of heat. Okay, especially if we do not have LED lamps, like diode emitter lamps, we may have the old one that heat more the space, so consume more, but also heat more the space. And so if you see that applying internally LED lamps will reduce potentially the byte consumption in terms of cooling or cooling requirements. Okay, that is visible in this sense for the left with the HVAC on, here HVAC off. Clearly we see in this case the comfort category, and and according to the EN 16781, so adaptive thermal comfort mode, and we immediately see that the touch mechanical ventilation unit drastically reduce the discomfort in winter, okay, in free running thanks to the heat recovery, but also has an impact on the category 1, but also has impact on other category, potentially moving the heat to other ones. So roughly speaking, it's clearly that in the climate point of view, the summer impact of touring is not so high, also with the recent typical meteorological year like that one, okay? Because, roughly speaking, typical touring climate in summer is hot, but not so drastically hot to bring the need for advanced cooling system like it is now in very, very recent years. In addition to that, it's also very evident how the adoption of an insulation wall and the adoption of touch mechanical ventilation system with heat recovery is very impacting on the heating needs, which is the majority one under this climate database, that support the fact that we have a greater reduction for specific thickness in turn also for reduction in investment. So we can go in 50 centimeters, not potentially to get the best, but in reality, when we pass from 15 centimeters, we will not reach a better, we can say, thickness after, because we pay more than what will be the benefit in the next 20, 30 years. So we look at payback time of 36 years in this case, and we can continue with other characterization that may suggest what may arrive. For example, solar shading is perfect. We reduce solar gains in summer. Clearly, they are controlled, so we're not bright in winter. Okay, but they may also adapt with the test that we've done in terms of controlling during the neutral season, with potentially a slight increase or slight cooling behave in the intermediate season, not before the full summer, May and September. And similar to that, you may see that lighting system has very high cost-benefit ratio. That's also because we set 200 lux per square meter, that potentially in residential may be less. Okay, but roughly speaking, this is what is suggested. And also is evident like natural ventilation, will work very well under a good control logic, but clearly when there is no control, it's more manually operated like we have simulated, maybe not the best strategy for some of the cases. When we pass to the actual meteorological here, we see, if we compare to the slide before, some changes. And these changes arrive mainly to the fact that the drastically higher temperature that we envisaged in recent year will have a strong impact on the result because we have summer discomfort. Okay? And this clearly will suggest that it's true that in typical meteorological year we do not have so many summer needs, so we can adapt and optimize the building, but the trend in some way will suggest that for future year we may also need to take more in consideration summer discomfort, okay? Because we imagine in this case in 2022-2023 here more than 1,500 hours of discomfort in summer. In addition to that, clearly this supports the fact that we see that the post-optimal that we had before in thickness insulation, 10-14, okay, is roughly speaking confirmed, but when we go higher than 40, we start to have problems in terms of summer load, okay? So, roughly speaking, what counts in the previous analysis confirmed it there, suggesting that potentially we can move to 12 and in the middle of this cost optimal of our operating flow. In addition to that, if we look, window replacement is very impacting in this case in winter discomfort, but clearly may support some extra heating during summer, like it is envisaged, for example, in a very hot and very cold climates like Switzerland. Okay, so the climate change will support this main approach that we ask for increase in ventilation domain. Like in these cases, with current condition, natural ventilation is very, very welcome because will block or will dissipate this extra cooling needs required in summer by this retrofitting analysis under the specific climate conditions. But clearly, when we come back to the topic and to the system itself, not only we can do this type of analysis, but we can also look inside the energy needs, the cost optimal needs, and what arrives in the sensitivity approach. So, for example, top left, according to the wall insulation thickness of the insulation layer that is under, we can see the drastic reduction of the heating needs. That is also interesting to see that clearly arrive as expected very fast in the first centimeter of insulation when the U value drastically fell down, and after it's slightly reduced because again the U value is reducing less with increased domain insulation. In addition to that, you see that the cooling as the sort of strange shape is slightly become up at the end, like is also shown in the literature in general. And on the natural point of view, we also see this impact of lighting approach. When we pass to the return of investment, we also see that clearly we can have an idea on the return on investment in terms of here with respect to the primary energy, the wall insulation thickness, suggesting now the identification of sort of cost optimal, at least having an idea of a single action and the multiplication of action from the table may be combined. In addition to that, we also see, for example, in this case, the extrapolation, but all the simulation, the package of simulation that was done of the window system, in which is clearly visible now, in respect to energy, cost, and type of window applied, the supported for primary energy to heating and cooling. You see that it's slightly different, the total, because this final energy with respect to primary. Okay, so there is the factor applied in this case to the primary one. And in this case, we also see that the cost, the cooling growth. So we demonstrate what we have, let's say before. If you look at the lighting system impact, for example, it's clearly evident. You will see that the cost for here working of this approach, the consumption of the lighting, and the total cost variation on the top left. And here on the top right, we have the return on investment variation according to the renovation action that we see, broadly speaking, all together. Okay, the variation of the efficient system COP will have this return on investment quite visible. The lighting system also because cost less. And intervention, so as the directly visible element, the wall is very visible. The floor insulation in this case is not so visible because it's very compact building in some way. So it's estimation is small. It's more complex to install the floor insulation than the benefit itself, and so on. And roughly speaking, here we have the difference between typical and the actual methodological here in terms of consumption currents, only mechanical ventilation, and the adoption of mechanical plus neutral ventilation, which in reality is the support of ventilative cooling. Okay. In addition to this, the system also allowed for all of the simulation that was done, okay, to see deep analysis when needed. It's automatically saved time series and plots under request. In this case, we see an example of simulation one, so of non-mechanical mode on, so cooling system on. First case typical, the second is the actual, one of the optimal. Okay, and you immediately see the variation in terms of carpel plots, now the predicted mean mode distribution, and you immediately see now that's quite positive here. We may have slightly cold in this period, okay, and after the actual, which is hotter, okay, it's larger the amount of full predicted mean mode. When we go to the indoor operative temperature, we also see the impact, the negative in this case, impact of the actual meteorological year, which is considered in terms of temperature because the cooling system is larger. Okay, that's what you can see. But roughly speaking, we can also see the energy signature that allow to plot energy need with respect to the outside temperature. Okay, in this case, and so you see again that the signature, roughly speaking, is slightly maintained, like expected, at least for heating. Of course, cooling is a bit less, but cooling, you know, we also have the there's the solar radiation and the ventilation variation that is added, so that's clearly may have some changes in this. But it's clearly evident that also we move the outside temperature from 25 to 30, 32, etc. in the average point of view for weekly days. In the case of free-running mode, we pass to the indoor operative temperature because there is no sense to have predictive involved, which is for mechanical building driven. And we see also on the Givoni classical carpet blocks that the climate is moving to resilient in the cooling period, with evident passages from this part to that part of the diagram. And it's also evident that we have here a large number of hours, which is below the comfort category in that thermal comfort mode, even category 1, always maintained, while with after climate heat waves, we go also in some cases to category 3, okay, but maintained with the ventilation in this sort of comfort domain that without will also spread out. So, broadly speaking, to conclude and to check if we have questions, is clearly that this type of tools is needed in some way, okay, because how we can have this type of analysis without a sort of automatic or semi-automatic tools? Now, it means that or you go with a basic tool to run manually thousands of simulation, or you need to use very simple tools that does not clearly have the power to manage a large amount of simulation, and potentially allow you to have some optimization, some suggestion, but does not compare in heat maps or this type of graphs. Then we also have the need and the possibility in this case to differentiate the key performance indicator according to the specific building, and also to have a very large amount of action that generally you don't see also in advanced commercial tools like controlled shading, like early controlling scheduling domains or set point domain for ventilation and so on, because this requires to have a dynamic simulation approach. In addition to that, clearly, it's very important that this type of platform that we see now is quite user-friendly. We do not have clearly the commercial graphical user interface like university. Okay, so we're at a certain point that clearly may support in future integration in other tools. But it's clearly possible to see that it's quite simple because the JSON is based on predefined action. You don't see coding or advanced coding approach or requirement to identify how the model is built for now changes the parameter of ventilation control or the thickness of the insulation. The platform supports you that for you. And in addition to that, it's true that we suggested to have a calibrated model at the beginning because we have immediately see that this will drastically drops down performance gap in previous analysis. Okay, so to have a model that reacts really simple and similar to how the real building do. It's also true that this is not always possible. So it's possible clearly to this analysis eventually to see a large series of variation, and analyze if the central one is roughly speaking aligned with expected consumption. But it's also true that we can also develop, and we have developed a very fast monitoring approaches to have an initial calibration of few days of monitoring under specific conditions. That would not be the best, but at least orient the simulation in the right dimension. Clearly, this requires transdisciplinary knowledge in the building domain, and also require the need to support further development of these approaches. But this is very welcome because also allow to test eventually the resilience of the choices under climate change, like we will do potentially inside the project, and also under specific conditions, like for example heat waves, another topic like this one that are very, very investigating now from the international energy point of view, and etc. So I think that now we can clearly pass to the potential question and answer session. I will start with one to Valentina to broken a bit, the starting point, and that's about you clearly show, Professor Stojceska, you clearly show to us the impact that European policy is pushing in the retrofitting domain. That, roughly speaking, we expect to have net zero 2020 for new buildings and 2050. That is true is 25 years from now, okay? But 5 years from now in the building domain is very small, like amount, because retrofitting means 5 years of work, 3 years of work building. So so it's quite near, that we arrive to net zero energy as requirement. Again, in this sense, how do you think would be the impact of these choices? How big will be? Because if we think at the Italian sector, this means, I don't know, many trillion of euro investment by private people to pass to the net zero energy, no? In these terms, I don't know what it is in the UK domain, but potentially a point of reflection on that is very welcome. Also to support all this, how big is this potential transformation, also in terms of life cycle assessment. So why it is so important, and why potentially Europe is pushing in looking at the extended environmental domain right now.
Okay.
Yes.
Can you hear me?
Yes.
Giacomo, if I understood correctly, yes. I think that retrofitting of the buildings will depend on the type of the building. And in my presentation, I mentioned that there is a huge difference when we are talking about retrofitting of the old buildings and the new buildings that are built now. Every building is different. Every building has a different approach. And if we take, for instance, an example of buildings that we have in PRELUDE project, we have about 5 buildings, and they're all different. They are old, but they have different. They need different retrofitting. They have different requirements. The way how they're dealt is different. Some of them are introducing more renewable energy. Some of them are going with a different approach. So the other thing, I think, which means the other thing that we need to take into account is the climate change. And we can see that there are different, what has been appropriate for retrofitting of the buildings years ago, or 5 or 10 years ago, maybe is not applicable anymore, because there is a change of the climate. And in some regions, we are having much higher temperatures. In some regions, we have lower temperatures. So that's also something which needs to be taken into account. And we have a complex process. It's not just to do something, but how to do and what is applicable for each building in each regions. That also needs to be taken into account. I'm not sure I'm responding to your question, but this is from my side.
That's clear for me. Yes, thank you.
Maybe if I can add something, I would say we will need also the person to make the project and realize them. So engineers, architects, and also to have the materials. And yeah, all aspects of the realization of the project will have to be taken into account, and yeah, to help that.
Yes, that's totally true. And in fact, one point that is, I think, very interesting of the EPIQR tools is that we know when we work as or when we speak with professionals, okay, is the complexity of making this analysis and the cost. So you think potentially not all of the retrofitting will go to a public building, very large, so millions of euro retrofitting work. Maybe also a residential, medium or small, okay, in which clearly making CO2 analysis will risk it to be, very expensive, very long, very complex in some way, because clearly required to have an idea of the material databases, and etc., etc. So my question to EPIQR is, how do you think would be fast? So in terms of professional use of this tool, because it clearly looks to be very interesting because it's quite fast, at least for having an analysis, but we can expect that for residential, we don't need to do, also because when we do the permission, it's not like, with the extra building, we don't pay an architect 100,000 euro, okay? We pay small to it. So how do you think would be the possibility of EPIQR tools and other tools that potentially will arrive in Europe for this type of analysis in terms of time needed to do the analysis? And this is clearly also a question for Valentina in some way, because it's how do you look, in this case, the development of the need for new tools, new graphical user interface new smart databases in Europe development. No? So it would be also the integration of in between informatics domain and building domains to have this sort of supporting tool that potentially would be needed for so large changes.
The use of all these softwares they have some limitations, still have some limitation. It has been lots of improvements in the past. I mean, at least now we have a database that we can use, like for instance, EcoInvent, but they're still kind of limited. And we have most of the data that we have, it's for the static life cycle assessment, if I can say. And but we need also to consider more dynamic life cycle assessment. For instance, what's going to happen with a certain building after retrofitting or after implementation of renewable energy in the next 5 to 10 years. And also we have to take into account we need to take into account the climate change. When we talk about the available data, we are still kind of limited with the data. As I said before, we need to, for each building needs different measurements to be taken. But what is important to have historic data, and that's not something that we can get it easily. We can get, yes, if, for instance, let's say we talk about only energy or water, for instance, the utility bills are available. But if they are not available, and if we take into account, for instance, the other elements that are affecting the environmental sustainability, that's also could be a problem. But what I would say, we are in a much better position than we were in the 5-10 years ago, but still there is work that needs to be done.
Okay, thanks. Do you have other questions? Okay, so we do not have question. Really, thank you for being there. Thank you to Nathalie Dumas from ESTIA and from Professor Valentina Stojceska from Bull University for being there, for the speech, okay, for the discussion. And for all interested, we will see in the 16th of January with the second part for the next event that clearly will be, in this case, will be more about, as we just said before, smart building support. So we will focus on building monitoring solution and system, on practical, on logic, and on smart solution that clearly data-driven approaches in Smart Living Lab and some of the demo cases looking at very advanced testing and checking in how to merge white box, black box, and gray box models and building proactive control. Okay, thank you very much to all, and see you in the next event.
Thanks a lot, Giacomo, for organizing, and I wish you all the best to you and everyone who was present today.
Yeah, thank you, everyone, and have a good end of day.
Thank you. Thank you very much.
Bye.